All right, let's expand a little bit on what we did in class today. So we know that any derivative just measures the rate of change of a function, right? And that's the slope. The derivative just gives us the slope at any point. So we can use this idea to study motion of things. Generally, we just look at things moving either completely vertically or completely horizontally. Now, we're going to call the position function s. Right, so we'll say it's s of t, where t, the variable t, represents time. Okay, so in our activity today, we created position graphs of people walking back and forth, and we started talking about some of the necessary vocabulary. Two of the big ones that we're going to look at first are initial position and displacement. All right, initial position just means where an object starts. All right, where an object starts. Analytically, what we're saying is at time t equals 0, what's the position? Right? So we're saying at t equals 0, we're plugging 0 into whatever our position function is. That tells me where an object starts. Displacement, then, is where an object ends relative to where it started. It's how far we are away from our starting position. Okay. How far away from the starting position. Now, to calculate that, what we want to do is just find our final position and subtract our initial position. Now, I guess I should mention for initial position, most of the time we're talking about t equals 0. But I mean, we could be saying, well, we're going to start at t equals 1 or something like that. Okay, initial position could be somewhere other than 0. Right? Generally, we talk about initial position at 0, but it could be somewhere else. Right? So let's take a look at a couple examples of displacement real quick. So in this example, we have an equation that represents the position of a particle. We want to find the initial position of the particle first. So initial position means, well, I want to evaluate where we are at t equals 0. So I'm plugging 0 in for t. So we just get 4, right? 0 minus 0 plus 4. So my initial position is 4. But now this says find the displacement from t equals 1 to t equals 3. So what that's saying is, in the second part of the question, I'm starting at 1 and ending at 3. So I want to evaluate those two. So s of 3, 3 squared minus 2 times 3 plus 4. So that's 9 minus 6 is 3 plus 4 is 7. Then I will also need s of 1. So that will be 1 squared minus 2 times 1 plus 4. So 1 minus 2 is negative 1 plus 4 is 3. So I ended at a position of 7. I started at a position of 3 if I'm looking at just from 1 to 3. So my displacement, I just take s of 3 minus s of 1, and that will get me a displacement of 4 units. Okay, now that's not necessarily total distance traveled. Okay, what displacement is saying is I'm 4 units away from where I started. Okay, graphically, what we're saying, right? Here's a the graph of that function of x squared minus 2x plus 4, or t squared minus 2t plus 4. So that's saying I started 4 units away from the origin. Right? That's my initial position. Well, then I moved towards the origin a little bit. Right? So at t equals 1, we are at 3, right? A position of 3. And then here, I changed direction and started moving back to the right again. So here I'm at a position of 3, then at 3, I'm at a position of 7. So my displacement, I went from a position of 3 to a position of 7. My displacement is 4. All right. So I want you guys to take a second and see if you can try number 2 here. All right, first, initial position, where my particle begins at t equals 0. So s of 0 is cosine of 0. Well, if I'm thinking about my cosine function, right, on the unit circle, at 0, the x value is 1, right? So my initial position is 1. Now, we want to find the displacement from t equals pi to t equals 3 pi. So I need both of those pieces of information. Cosine of pi, well, on the unit circle, pi is all the way over to the left. So the x-coordinate there is -1. Then at 3 pi, well, 3 pi is 2 pi further than pi. So if I'm at pi over here, I go 1 full rotation, and I'm all the way back over here. Right? So cosine of 3 pi is actually the exact same spot as cosine of pi. It's -1. So my displacement, my final position, minus my initial position in this case, is -1 minus -1. That's -1 plus 1 is 0. I actually ended in the same place that I started, right? So visually, if we take a look at cosine, right, we're starting at 1, then at pi, I'm down here, right? I'm down at -1, and then at 3 pi, I'm also at -1. So even though I did a lot of traveling, right, my particle definitely moved a lot in between t equals pi and t equals 3 pi, I ended in the same place that I started. All right. So my displacement, we would say, is 0. All right. So this then is probably the biggest idea out of this section. Right? The rate of change of position. Right? So the derivative of position, we say, is our velocity function. All right, so in symbolic notation, I can say s prime of t is equal to v of t. Right? Now, we talked about this a little bit today when we did our position graphs, okay? But whenever my velocity is positive, right, if we've got something moving in a horizontal line, right, like what we were doing today, moving back and forth, if my velocity is positive, that means I am moving to the right. If my velocity is negative, that means I am moving left. Okay? This doesn't mean I'm speeding up or slowing down or anything like that. Okay? Positive and negative velocity just tell me what direction I'm going. Okay? So positive means moving right, negative means I'm going left. If my velocity is 0, that means I'm not moving at all. Okay? That means I am stopped. Similarly, if we're talking about vertical motion, like maybe tossing a ball up in the air, if velocity is positive, we are moving up. If velocity is negative, we are moving down. And if velocity is 0, we are stopped. All right. So big idea, the derivative of position is velocity. We're going to analyze a lot of velocity functions here. Now, we're going to go one step further, okay, and also analyze the derivative of velocity. So the rate of change of velocity is acceleration. Whoops. There we go. So in symbolic notation, we can say the second derivative of position is equal to the derivative of velocity is equal to acceleration. Now, acceleration, if we want to talk about positive, negative, and zero acceleration, this is a little bit trickier to visualize, okay? But I think it'll make more sense in a second. But let's fill out this chart first. So if acceleration is positive, okay, for a horizontal line, that means that the object is being pushed to the right. Okay, that doesn't necessarily mean it's being, or it's going to the right. It's not necessarily going in that direction. It just means it's being pushed to the right. Okay, there's a force acting on it, pushing it to the right. So even if my object is moving to the left, I can still have a force pushing it to the right. If my acceleration is negative, I am being pushed to the left. Now, if acceleration is zero, that doesn't mean I'm stopped. Okay? If acceleration is zero, that means velocity is not changing. Right? Or we can say velocity is constant. Right? Similarly, in a vertical line, and I think this one might be a little easier to visualize. If acceleration is positive, that means we are being pushed up. If velocity is if acceleration is negative, we are being pushed down. And again, if acceleration is zero, velocity is constant. So a good visual here is if I throw a ball up in the air. Well, if I throw a ball up, okay, we would say its velocity is positive, right, because it's moving upward. However, its acceleration is negative because gravity is pushing it down. Okay, that's I think maybe the best simple visual of what we're saying here. All right, so those are the big three: position, velocity, acceleration. Those are the ones that we are going to take a look at in detail, ask most of the questions about. There are a couple others, though, that have names that are kind of interesting. This one you might see a little bit. The derivative of acceleration is actually called jerk. So here we could say the third derivative of position is the second derivative of velocity, is the first derivative of acceleration, is equal to jerk. Now the next three, okay, so the fourth derivative of position, which would be the first derivative of jerk, is actually called snap. The fifth derivative of position is crackle. And the sixth derivative of position is pop. I'm not making this up. Right? This is true. I do not know which came first, these names for the derivatives or the Rice Krispie slogan. Okay, but this is real. Okay, the third derivative of position is jerk, the fourth is snap, the fifth is crackle, and the sixth is pop. All right. You'll probably never see these three again. That's just an interesting tidbit, but you will definitely see position, velocity, acceleration, and sometimes jerk. All right. So another idea that we're going to look at more in depth tomorrow, but I want to introduce it now, is speed. All right. Now, remember, velocity has direction. Okay, direction matters when we're talking about velocity. Direction does not matter when we're talking about speed. So speed has to be either positive or 0. So the way we define speed, okay, is just the absolute value of velocity. Right? It's just our directionless velocity, basically. And we'll take a look at this idea in a lot more detail, mostly from graphs tomorrow. Right? We will take a look at it a little bit today, right? But let's then take a look at this idea, okay? Speeding up and slowing down, okay? Those are a couple of big ones. I can pretty much guarantee you on the AP test, at some point you'll be asked if an object is speeding up or slowing down, okay? An object is speeding up if the velocity and acceleration are going in the same direction, right? Meaning, if I'm moving to the right and my force is pushing me to the right, then I'm speeding up, right? If I've got a positive velocity and a positive acceleration, my object is speeding up. Same though if they're both negative, right? Negative velocity just means I'm moving to the left. Negative acceleration means the object is being pushed to the left. So if both of those things happen, my object is also speeding up. If my two things are working in opposite directions, then my particle is slowing down. Right? If my object is moving to the right, but acceleration is pushing it to the left, then it's slowing down, and vice versa. If my object is moving to the left, but acceleration is pushing it to the right, it will be slowing down. So if position and velocity, if velocity and acceleration have the same signs, the object is speeding up. If velocity and acceleration have opposite signs, our particle is slowing down. Okay? So let's jump in and take a look at all of this information in a couple of example problems. So let's go through all of number 1 together, and then I'll have you guys try number 2 piece by piece, right, and answer the questions on here. So first, here we've got a function 1/3 t cubed minus 4t squared plus 7t plus 3. Our first goal is to find the initial position. So I want s of 0. So if I plug 0 in, I'm not going to bother writing all that out, right? This will be 0, this will be 0, this will be 0. And we just get that we are starting at 3. Our initial position is at 3. Then we want the particle's displacement between 1 and 3. So I need to evaluate s of 3 and s of 1. So I'm not going to bore you with plugging all that in. If we actually plug these in, we get -3 and 19/3. So my displacement then is final position minus initial position. So s of 3 minus s of 1 equals -3 minus 19/3. So what is that? -28/3. Now, does it make sense to have a negative displacement? Well, sure. If we think about our function here, this is what this function would look like, right? Starting at 0. So at 1, I'm right here. And then I'm moving to the left, right? I'm moving to the left all the way here, and my position then at 3 is -3. So that negative displacement is just saying I moved to the left 28/3 spaces, or it's -9.33333, right? So part C then and D want us to just find velocity and acceleration functions. So if this is my position function, velocity is the derivative of position. So s prime of t will be my v of t. So I'm just taking my derivative. So 3 times 1/3 is 1. So we just get t squared minus 8t plus 7. And then my acceleration function would be the derivative of this. So s double prime of t equals v prime of t equals a of t. So this derivative would just be 2t minus 8. So that's my velocity and acceleration. Now, part E then says find all times when the particle is at rest. Okay? At rest, okay, or when a particle is stopped, means the velocity is equal to 0. Okay, we talked about that idea a little bit back here in the table. Right? We said v of t equals 0 means the particle is stopped. So this is a common question to be asked. Find times when the particle is at rest or stopped. So we want to take our velocity function, right, which we said was t squared minus 8t plus 7. So t squared minus 8t plus 7. And we want to set that equal to 0. So this is a quadratic. It's already all on one side. We want to see if it factors. That's the easiest way. I think this one does. Okay, if it didn't, we would just use quadratic formula. But I think this will factor, so two numbers that multiply to positive 7 that add to negative 8, I think would be negative 1 and negative 7. So setting those equal to 0, we get t equals 1 and t equals 7. All right. So those are the two times when the particle is at rest. It's stopped. Right? The velocity is equal to 0 at 1, and it's equal to 0 at 7. Right? So visually, if we go back to our graph, what we're saying, remember, velocity is the slope of position. So if this is my position graph, we want places where the slope is 0, meaning we have a horizontal tangent line. Well, that happens here at 1, and it happens down here at 7. All right? So we go back, let's take a look at part F. Find the position and acceleration when the particle is stopped. So what this is saying, okay, we already found that the particle is stopped. This happens at t equals 1 and t equals 7. So all I want to do is plug those two values into my position and acceleration functions. So s of 1, s of 7, and a of 1, and a of 7. All right, so again, I'm just going to go back to the graph to get my two values for position. So at t equals 1, well, that value, we actually already found that in another part of this problem, right? It's 6.33333, or 19 thirds. And s of 7 then is negative 29.66666. So what is that? Negative 89 thirds. Then my acceleration, okay, we haven't graphed this, but my acceleration function is pretty straightforward, right? It was just 2t minus 8. So this will be 2 times 1 minus 8 is negative 6. This will be 2 times 7 minus 8, which would be 14 minus 8 is positive 6. Okay, so questions like this may show up where we're just asked to find, position and acceleration at random times, maybe when the particle stopped or when velocity is equal to 2. I mean, something like that. All right. So parts G and H then say find the velocity, speed, and acceleration at t equals 2. Okay, so I just want to plug 2 into my velocity function. Right? We said my velocity function. So yeah, I'll go ahead and write it out. So my velocity function was what? T squared minus 8t plus 7. Is that right? Yeah, t squared minus 8t plus 7. So I want to evaluate this at 2. So v of 2 will be 2 squared minus 8 times 2 plus 7. So we get 4 minus 16 be negative 12 plus 7 is negative 5. Now speed, we said was just absolute value of velocity. So speed is absolute value of velocity. So the speed at time t equals 2 is going to be positive 5. So I guess I'll write it like this. Speed of 2 equals absolute value of v of 2, which would be absolute value of negative 5, which would be positive 5. Okay, so what this tells me, velocity says I'm moving to the left with a speed of 5. Right, so my speed then is just 5. And then acceleration at t equals 2. So a of 2 will be 2 times 2 minus 8. Right, because my acceleration was 2t minus 8. So we get 4 minus 8 is negative 4. All right. So then lastly here on this first example, we want to know, is the particle moving left, right, or stopped at t equals 2? Well, to do that, I just want to look at the velocity at that value. Okay, remember, we look all the way back at my chart up here. Right? If velocity is positive, we're moving to the right. If velocity is negative, we're going left. And if velocity is 0, we are stopped. So, at t equals 2, we just determined that the velocity was negative 5. That means at t equals 2, since it's negative, I am moving to the left. Now, is the particle speeding up, slowing down, or remaining at a constant speed at t equals 2? This, remember, you need to look here. If velocity and acceleration have the same sign, we're speeding up. If velocity and acceleration have opposite signs, we are slowing down. So, here we've got a negative velocity and a negative acceleration. That means we will be speeding up. Okay, we will be speeding up in the left direction, okay, but we will be speeding up since both velocity and acceleration are negative. We're moving left and we're being pushed to the left. Okay, so I want you guys now to take a look at number 2 and try this one. Now, this one, first part, I guess, is a little tricky because we have a log function, which means we have to say that our variable is greater than 0. It can't equal 0. All right, so I guess let's just do part A together here. Since it can't equal 0, right, the initial position, right, we would technically say that if we plug 0 in, it's undefined because the natural log of 0 is 0. But what we can say here, if we think about, or if we look at the graph, right, this graph does actually start at 0. Right? Even though 0 isn't defined, right, we would still say that this starts at 0. So even though my s of 0 isn't defined, we're going to say that my initial position is 0. And I'll just kind of put that in quotes because we know that that's not a value that's included on the graph, right? But it is where we're starting. So you guys go ahead and take a second and try part B here. Okay, displacement. Remember, we want to evaluate s of 1 and s of e. Right? So if I plug e in here, I will have e times the natural log of e. Well, e obviously will stay. Natural log of e is just 1, right? So we have e times 1, so s of e equals e in this case. Now if I plug 1 in, I've got 1 times the natural log of 1. Natural log of 1 is 0, so 1 times 0 is actually 0. So my displacement then, s of e minus s of 1 is e minus 0, which is just e. Right? So my displacement is e. So if we look at the graph, right, we're saying at 1, where the position is 0, and then over here at e, we're saying its position is actually also e. So we traveled a distance of e from 1 to e. All right. You guys go ahead and try to find my velocity and acceleration functions here. All right. Velocity is the derivative of position, so s prime of t equals v of t. I have to use product rule here. T times the natural log of t. That's two functions being multiplied together. So derivative of the first is 1 times the second plus the first times the derivative of the second. So derivative of a log is the derivative of the inside over the inside times the natural log of the base, but natural log of e is just 1. So I can actually clean this up a lot, right? This would just be natural log of t. This would be t over t, which would just be 1. So now I want to take the derivative of this, right? So second derivative of position is the first derivative of velocity is acceleration. So the derivative here, natural log, derivative of natural log is 1 over t. Derivative of 1 is 0. So my acceleration is just 1 over t. All right, you guys take a second and try to find all times when the particle is at rest. All right, so remember, at rest means velocity is equal to 0. So we said our velocity function was the natural log of t plus 1. So let's solve this for t. Subtract that 1 over first, so I'll have natural log of t equals -1. Now, to undo a log, I want to raise both sides to be a power of the base, right? So the base is e. The base of my exponential then is going to be e. So I'll have e to the natural log of t equals e to the -first power. Now when I do that, the whole reason I do that, e to the natural log of e, or to e to the log base e cancels out, and we just get t over here. So I get t equals e to the -first, or I could rewrite that as just 1 over e to the +1st. Okay? That's my only time when the particle is at rest. All right, you guys take a second and find the position and acceleration when the particle is stopped. All right, so what that means, we want to evaluate s of e to the -first and a of e to the -first. So if I plug this into my original function, well, my original function is just right there. So e to the -first times the natural log of e to the -first. Well, if I simplify this, e to the -first, I could leave it as e to the -first, or I could write it as 1 over e. Natural log of e to the -first. Well, natural log of e cancels out, and this ends up just being -1. So I could just write this as -1 over e. Now my acceleration function was 1 over t, so this will just be 1 over e to the -first. Well, that would just be e, right? I can bring this to the numerator and make the exponent positive. All right. Now, you guys take a second and find the velocity and acceleration at t equals 2. All right, so velocity was natural log of t plus 1. And I can't really do any simplification. Right? I'll just leave it as natural log of 2. I could put it in the calculator and get a decimal, but we'll just leave it like that. Speed then, so speed of 2 is equal to the absolute value velocity at 2, which equals the absolute value of natural log of 2 plus 1, well, that's already a positive value, so the speed is actually also natural log of 2 plus 1. Then the acceleration at 2, so a of 2, our acceleration was 1 over t, so we just get 1 over 2. All right, and finally, take a second, try I and j here. All right, so is the particle moving left, right, or stopped? To figure that out, we just want to look at our velocity. Velocity is positive at t equals 2. If velocity is positive, that means my particle is moving to the right. Then is the particle speeding up, slowing down, or remaining at a constant speed at t equals 2? Well, remember to do that, we want to look at the signs of both velocity and acceleration. In this case, they are both positive. If they are the same sign, that means we are speeding up. Okay. All right, that is it.